I'm Albert. I worked as a CCA predoc with Mateo, and this is the project I was involved in, with a long title. But yeah, the main word you should take from here is hot Jupiters. So I'm going to first give a brief introduction about hot Jupiters and what evolutionary models with MESA we've been playing with, and then the Rossby number estimation inside these hot Jupiter models, and the magnetic field predictions and observational consequences. And if I have time, I will give what I'm doing now, which is about taking these results and putting into a 3D simulations. So what are hot Jupiters? Hot Jupiters are planets. This is the exoplanet population taken from NASA a few weeks back. And this is the mass and the orbital period. The mass and the orbital period. Hot Jupiters are low period and high mass. Are like Jupiters that orbit close to their star. One other property is that their eccentricities are low, because whenever an object orbits close to their star, the tidal interactions are strong, and there's a process called tidal circularization that usually makes these eccentricities go to low values. So, and the last property is that they mostly orbit F, Gs, and K type stars. It's the peak of occurrence rate. There are some in orbiting M stars and some orbiting A stars, but the bulk of them is F, G, and Ks. So this plot is a bit complex. Here is the flux that a planet receives on the y-axis, and the x-axis is the orbital period. So for a given flux and a given period, you can associate a main sequence stellar type. And those are these color lines, are the different stellar types. And here on top, I'm going to plot the hot Jupiter population, and you should expect them to be in the F, J, and K type stars, and they are. On top of it, I'm also plotting the synchronization timescale. What is the synchronization timescale? Is the time it takes to circularize the orbit. And this was just to confirm that, yeah, hot Jupiters are tidally locked. Sorry, I said tidal circularization is tidally locking. Yeah, this line is the line where the synchronization timescale equals the main sequence star, meaning that every planet on the left is tidally locked or will have time to get tidally locked. So apart from these three things, they're highly radiated and tidally locked and low eccentricities. There's one other fact, that they are more inflated than they should be. This is a plot showing the black line showing the only irradiated models, the radius of the only irradiated models, meaning that hot Jupiters are found to be higher than only irradiated models expect. And there are some papers out there that give this epsilon, which is the heating efficiency, that it's the percentage of heat that the planet receives and is deposited inside. So the planet gets inflated. I will talk about it in a moment. But yeah, here on the right, I'm showing you my own models are the lines. These models are only irradiated models. And you can see that most of the real planets are above it, meaning that this planet needs some kind of mechanism to heat them up and inflate them further, not only radiation. So what did we do? Well, we took the MESA code, which I'm sure everybody here knows what MESA is, and we evolved these models where the energy equation has not only the irradiation term, but also the heat term. So what's the total deposited heat inside the planet? It comes from these observational models. And yeah, we calculate the flux, and with this heating efficiency, we put it inside the planet. And with these models, we want to try to answer two questions. How do the interiors of hot Jupiters change, the dynamics, and what are the magnetic field predictions? So what did we do is we took, for example, one solar mass star, a G2, this one here, and we took, like, for example, 50 different hot Jupiters orbiting around it, all of them tidally locked. And after applying the heat, instead of the radius being here around 1 Jupiter or 1.2 Jupiter, it jumps up to 2, which is the observed values. So here I will explain what is the interior structure of a typical planet. You have the planetary radii followed by the irradiation layer. That's where irradiation stops. It depends on the opacity. And then you have the radiative convective boundary, below which all the planet is convective. And there's another thing which I'm calling dynamo region, which it doesn't come from MESA. Actually, I'm associating it when the pressure reaches 1 megabar, which is where hydrogen goes from molecular to metallic. And before I go further, what is this dynamo region? Every planet, most of the planets have active dynamos inside. And for example, for rocky ones, you have a molten iron interior that when it convects, it creates a magnetic field. But for gas giants, it's not molten metal, it's metallic hydrogen. And yeah, these predictions of metallic hydrogen existing inside Jupiter and Saturn predict well how the shape of the magnetic field is. So yeah, okay. And the question is, where did we put this heating? Because usually, when people do these kinds of heating models, there are several for example, ohmic tidal or atmospheric dissipation models. Usually, these models apply the heat in the outermost regions. But when people try to make magnetic field predictions, they are optimistic and they assume that all this heat enhances the magnetic field. And this would mean to heat in the dynamo region. So here we do the two extreme cases. Either all heat is applied in the dynamo region, or all heat is applied outside the dynamo region. If all heat is applied outside the dynamo region, you will get poorer magnetic fields, as I will show you in a minute. And if you apply it inside the dynamo region, you will optimize the magnetic field predictions. So these are examples of the radial models that we get. Yeah, I'm showing both the only irradiated and the irradiated plus heated. And you can see, for example, for 4 different periods. You can see that the closer you are, the more expanded you are, and the bigger difference. Here is the purple one. The only irradiated purple one is here, and only irradiated purple one is way more inflated. Here, I just want you to look at what I'm plotting here below. It's the convective velocity, which is derived from mixing length theory, which I will use in a moment, and the scale ratio. And also, yeah, the convective flux, which is defined as this. The convective flux is used for the magnetic field prediction, and these two are used for the Rossby number prediction, which I'm talking about now. What is the Rossby number? The Rossby number is the quotient, the ratio between inertial forces divided by Coriolis forces, or in other words, the rotational timescale of a rotating planet over the turnover timescale of its convective region. Why is it important? Because usually planets are in the low Rossby number regime. And this low Rossby number regime always optimizes the magnetic field predictions. And there are some papers that give scaling laws for rapid rotating bodies. And yeah, for simulations, it works very well. And for observations, it works well in the rapidly rotating bodies, for being the planets and the rapidly rotating stars or young stars. Other stars start to fall. So it's important to know if planets are actually in the rapidly rotating regime. So when calculating the Rossby number at each planetary depth and for 50 different planets, for example, I recover these kinds of plots. And these kinds of plots, what you notice is that the Rossby number below this dashed line inside, it's below 0.1, meaning that it belongs to the rapidly rotating regime. And yeah, these 2 panels on top and 2 panels on the bottom are the same, but I'm only changing radius and pressure. Why? Because if you put pressure, you can look more clearly at the atmosphere, but if you put radius, you can physically see how much bigger the dynamo region is. But yeah, the main conclusion is that all the dynamo region in both the inflated and non-inflated models still are in the below 0.1. So they are still rotating, rapidly rotating bodies. But what happens? Yeah, sorry, I forgot to say that these plots are when the heat is applied internally. What happens if I apply it externally? Here it's applied internally, and here is applied externally. When you apply it externally, the heat deposition makes the same planetary structure, but it changes the convective velocity in such a way that the entropy stops being flat throughout the planet and starts having some positive gradients. And these positive gradients lead to the breaking of convection. So what you see here, for example, this is a planet at 5 days. Inside of it, there's a region where the convective velocity is 0. It's not defined, so you cannot get a Rossby number. And this will be crucial for the magnetic field predictions. Yeah, these are for K, G, and F stars, all the stars in that the main hot Jupiters populate. And this was just to see that no matter what kind of star it is, still you are in the rapidly rotating regime. We only found a couple of exceptions where the Rossby number here, it's above 0.1 or even above 1, which is for the large planets which are orbiting far away from the star. Far away, but still tidally locked. And some people would not even say that they are hot Jupiters. In this case, it's about periods of 30 days. And you can see that a chunk of this 12 Jupiter mass planet is above 0.1. And it actually doesn't matter very much, because if you search for planets below 4 Jupiter masses and between these two periods, you will only find 3 cases. And yeah, 2 of them are quite far away, so the radio emissions that you could expect for them are non-detectable. But yeah, at those orbits, you could even argue that maybe they are not tidally locked. So I wouldn't. Yeah. But the conclusion is that all observed hot Jupiter planets remain in the fast rotating regime, because most of them are not above 4 Jupiter masses. Most of them are below. And these are only the 3 cases that I could think that maybe they could be slower in the slower rotating regime. Yeah, and to finish, with those magnetic field scaling laws that I told you before, you can get magnetic field estimates with some formulas from this paper that everybody uses. And yeah, you can have the prediction that you want. If you only irradiate it, you will find a slow decay, which it also happens if the planet slowly shrinks, like a cold Jupiter. If you heat it, the heat involved will dominate over this cooling, and it will just rapidly reach a steady state. And these are the predictions that optimistic people use to point the radio telescopes to the hot Jupiter targets. But what I'm saying here is that if you apply this heat externally, which most of the physical mechanisms of heat deposition actually do, that you break this interior convection, and then this integral over the convective dynamo region falls. Actually, I'm showing here the magnetic field at the dynamo surface, and it's quite high. It's 900. But actually, what you will find in the literature is that they predict about 100 for the most optimistic cases, which is here. Because this is the equatorial component at the surface, which is calculated with this factor. And these would be the observable numbers that you would calculate your radio estimates with. Yeah, and finally, the radio estimate, for the observational people, we thought it would be nice to give estimates for the available star-planet interaction processes. This one is famous, Lanza 2013, and it's famous because a group in 2019 used it, and they claim that they measured the magnetic field of 4 planets, which a lot of people do not believe, but maybe, I don't know. But yeah, these are the predictions for these same models, and yeah, you can see that if this mechanism of external heating is true, you see like a 10 to the 4 decrease in this SPI interaction. This SPI actually, it's only the 2 magnetic fields of the star and the planet dragging along each other, and yeah, they create some available power which might accelerate particles and might radiate energy. And the last one is the ECMI, electric cyclotron maser radio emission. That this would not be like a star-planet interaction. This would be a radio wind interacting with the magnetic field of the planet. And there are scaling laws out there, and we used one of them to give estimates. And the same, if this, we recovered like very optimistic when we applied the heat internally, but if we apply the heat externally, there's a 10 to the minus, a factor of 100 less of radio flux. Yeah, and here are my conclusions that I won't go through them again, but what I'm starting to do now is apply these 1D models for a 3D project, which I already had one, and I don't think I have time to explain what I will do, because it's 0.
All right, thanks a lot. So any questions from the audience? And reminder, if you do have a question, to please pop up your seat mic. So I was actually wondering, so you mentioned this this epsilon, this distribution in FIR that looked like a log normal. So can you clarify where exactly that comes from?
Yeah, this is a study in 2018 where they took all the, it's a statistical study of taking all the hot Jupiters and with similar 1D models applying different functionals for this epsilon in terms of the flux they receive. And they find that a Gaussian is the best.
Okay, so that is subject to whatever selection function we have on these objects?
Yeah, they had an exponential, a log, and a linear one. Yeah, this worked quite simple.
Cool, thanks.
And we just took them from a paper. It's not our. Yeah.
Thanks. Lika?
If I understood you correctly, you said so there was another paper that claimed there was a detection of magnetic fields.
Yes.
But now you're saying that was impossible. They could have never seen it. Is that what you're saying? Or are you saying, well, we don't know?
Yeah, well, actually, the model that people try to believe most is the ohmic model, which relies on having an internal magnetic field that then, if you hit the external parts, you can kill again the internal field. Okay. And there you simply get like a less efficient dynamo. That would be also compatible. But yeah, it's just saying that everybody assumes that the magnetic fields are high because the areas are inflated and so on. But yeah, if we assume that the heating injection is external, we actually kill those. It was just don't be that optimistic about this.
Yeah. Okay, thanks.
Tobin, did you have a question?
Albert, I was a little bit curious on the impact that the star host had on the Rossby index and some of this fast rotating regime. So if you had something that's like dependent on the stellar type, that magnetic fields might interact, and if that changed your results at all.
Yeah, usually the bigger, here I'm showing M, MKF, MKG, and F. If you see, every time that you go to higher mass stars, the Rossby number is a bit higher. And you get to lesser and lesser fast rotating objects. But yeah, I didn't get numbers below. So yeah, the thing is, the lower the Rossby number is, the faster it rotates, and usually the more dipolar the field is. So yeah, the big question would be like, if these models were actually out there, these planets, maybe those fields would be a bit crazy, not like the Earth or Jupiter.
All right, thanks a lot.